practical kind of focus event on July 8th and 9th, as I said. So I invite all of you also to register for it, participate in that. Registration will be open possible. Particularly appreciate the initiative of developing the Telugu LLM, and of course, this is an opportunity which will help the next billion users of internet. Most of the next billion users of internet will be using it in their own language. They will not be knowing English. They will not be having any kind of advanced college degrees. They will be living in rural areas. So language should not become the barrier, and therefore the effort to collectively work on large-scale local language models is very noteworthy. We are also making similar efforts, and I'll be happy to kind of collaborate and synergize. We have got permission, so it has not yet been officially announced. We have got permission to access the database of a huge Telugu newspaper. This newspaper group has millions of articles, millions of publications, and the entire archive has been made available to us. So this again is a very good kind of resource for us to train our model and make it more and more accurate. Eventually, accuracy is what will push the needle. This voting solution that I spoke about, we have not been able to kind of scale it up or convince the election authorities or the election commission of India, because it is still not 100% accurate. So it is, the accuracy levels are very good, 87% or something like that. But till it becomes much more accurate, no one will really be able to give 100% confident kind of acceptance to it. So this is again something which we need to do collaboratively. We need to pool our resources. And as I said, I'll be very happy as the government will be very happy to support any such initiative which is going on. So once again, good wishes to all of you, and thank you very much for inviting me.
One small announcement. My request, Kiran Chandra, founder Swecha, Professor Pratap, President Swecha, Chaitanya, co-founder, CTO, Ozotel, Nagendranath Garu, Senior Advisor, Salamander Advisory Services, the Honorable Vice Chancellor, Kata Narasimha Reddy Garu. So if you can also please join us on stage for 1 minute. Raj Malladi, Vice President, Tech Mahindra, Srinivas Mohan Garu, again, there is no introduction. You've all seen Bahubali, RRR, Turado. He's the person behind all of that stuff.
We're going to set up a center here called as the Center for People-Centric AI. The spirit with which the conference has begun, solving problems for the commons. Thank you, JSRU, saying that he will be supporting us all through. He has been always supportive of it. And I think this center is going to look at solving problems for the commons. And I think all the scientific community that has been sitting here has listed close to 200 problems or odd problems since all the speakers were going on yesterday. So I think we'll start solving some of them, and hopefully we'll be able to present in the conference that is going to be there. And in these 3 months we have solved X number of problems.
We've already a few institutes, including IIIT, a few companies, they're also represented over here, signing up, universities and all. There are a few companies which have signed up to be founding members of this center as well. There's an open call. I know there are a lot of companies, startups, research institutes, including the likes of CCMB and others who are a part of this. We're also proud to announce that the Cyber Cell, they were there yesterday, the institute was there. They wanted to partner in the center that we are setting up as well. So if you're interested, please do reach out. This center over the next 1 year, we will be working towards innovation AI for society. Hubs will also be there across the area. This is not just, this will be centered in Hyderabad. We are opening up hubs in Madras, Bombay, Chennai, Mumbai, Bangalore, other places as well. This is going to be a huge initiative where we are going to be working on use cases. If you're wondering why we have this, we have demonstrated farming and agriculture use cases yesterday. This will actually be, we will be releasing lots of use cases as we go forward. This is an open invite. If you're representing your company, industry, startup, whatever it is, if you're interested in building people-centric AI solutions, please do reach out to us. We're going to be actually launching the center in a month's time frame, and we look forward to collaborating with you. Jayesh Garu has also said they're happy to collaborate with us on all of these things, and we'll be more than happy to work with the government and other organizations which are working with the vision of people-centric AI and AI for society. Thank you. Thank you. and then we have spoken about how AI is going to take over, right? We started to say something that we have built, executed with a vision towards AI. The AI vision was 2017 when we held the DevCon 2017. We've spoken about AI vision. 7 years later, why don't we, do a future perspective? Where do we think we'll be? I am quite sure we will be entering the era of quantum computing. So with that note, I think we should conclude the conference with Dr. Krishna Palam Garu, the founding CEO of AcceleQuant. He's going to be talking about the intersection of AI, ML, and quantum computing. Sir, I think you should please join us. And 7 years, 5 years down the line when we are here, that could be the current, that could be the present. Because 7 years ago we started talking about AI, ML taking over, and here we are today. Probably 5 years later we will be calling it AI quantum days or something like that. But nobody better than Dr. Krishna Palam Garu to talk about the intersection of AI, ML, and quantum computing. I know it's a very curious topic for all of us. Nothing better than you speaking to close this out. Thank you. Thank you so much for obliging and joining us over here.
This is on? Yeah. Okay. So I make you one promise. I will let you go in 25 minutes. You don't ask me any questions. And that's at the end of long 2 days. But this topic actually would have been done better than like early in the morning, because it can be quite confusing, and I'll show you why. I'll start out by giving you a 5 to 10 minute overview of what quantum means. Then we'll talk about what it really is used for and potentially in the AI space as well. So I'm right now running that company, so I don't want to go into the company specific things too much. So the spirit of what I do is just an overview of what's happening in the field. You see those words on the left, I'll walk you through those. Those are terms used very freely, quite often without attribution of what it really means. So I'll start trying to give you a feel for the basic vocabulary of what quantum anything is. And then we'll move from there to trying to see how we can use it. So these are cartoons which are very, very approximate. So you can easily misinterpret them, but I deliberately watered them down so that you can understand what the real meaning is. So normally we all know that there are things called bits that you compute with. Quantum lives in the world of something called qubits. So a bit is simply a 0 or a 1. And typically when you build these ICs, integrated circuits, of a semiconductor material, there is a high voltage or a low voltage. And this voltage can be thought of as encoding a 0 or a 1. Qubits are done in a much more complicated and even somewhat bizarre way. So, and this is where things could get inaccurate. You actually manipulate and encode information not at the level of charge, which is about, 10,000 to 100,000 electrons, which is called bulk charge, but you can start manipulating individual electrons. So a single electron, when you start moving it around, it really doesn't want to move around the way you want it to. So the way you can think about this conceptually, there's a lot of mathematics and physics behind it, is that black dot, if you want to encode the information on it, depending on its energy level, you use a tiny laser tweezer and actually move the electron to where you want it to be. And this now lives in a supercooled bath, which is held at a very, very cold temperature, and hopefully we can live there for some time. And that encodes your information. So the mechanism through which, and there are lots of different ways of doing this, there's light-based quantum qubits, this is superconducting material-based qubits, but there are different ways of building them. But they're all manipulating extremely fine-grained phenomenon, because I'm sure all of you have seen, whether you like it or not, some point, the concept of quantum in the physics world. So quantization really is quite old. What it really builds on is, by virtue of doing what we just said, you can stack these qubits and they can encode states that are much more complex than bits. That's about the basic idea. And so if you think about classical bits, each bit is a 0 or a 1. Depending on the number of dots, you take that many times 2, as a total number of possible combinations. In a strange way, because you're manipulating these electrons that can live in many states at the same time through this physics phenomenon called superposition, these internal states of these entities can simultaneously encode, you can imagine, many such strings. So many red strings can sit inside one green string. And that's the strangeness of quantum. So simultaneously, you're taking a stack and taking a red string, another red string on top, another, and you build a stack of it. Those all live in a single green string. And now you cleverly take the green string and compute by moving it forward to create another shade of green. That means you move the entire stack of reds simultaneously in some meaningful way so that the result is what you want. So you can imagine why that's not easy. And the way you do this, if you're a programmer, is you write this down as some sort of a matrix operation on another matrix. But if you're building a system, it's much more challenging. We'll talk about that in a second. So, and this is where it gets really interesting, and that's sort of where it stops getting really interesting. After that, it's basically exploiting what I'm about to tell you. These quantum systems obey something which is, and now confirmed by science, a phenomenon which is somewhat strange called entanglement. So a very crude and inaccurate way of describing this, but it gets the idea across, is if you have two electrons and they're entangled, one is pointing up, one is pointing down. The theory said that if you send one of these two electrons that are entangled to the moon, and then it sits on the moon, and then you change the electron that's pointing up to pointing down, the other electron will change its spin instantaneously. And this is so bizarre that obviously it raises objections. So I'll get to that in a second, but let me walk through why this phenomenon builds on something that's actually very significant, and it took a long time. So if you don't get it in day one, that's really no one's fault except that it's hard. So the initial model of the atom we all know, which my kids in 8th grade study, is called Bohr's atomic model. So Niels Bohr, the famous physicist, proposed this model where there are these electrons sitting in orbits, and there is a nucleus which is protons and electrons. So the time scale you can see for yourself. But the person who really triggered a very important break in this and led to what became the modern view of quantum mechanics is Schrödinger. So he postulated, and it's hard to explain this in 1 minute, but I can give you the idea. What he postulated was that at the level of an electron, when you take a magnifying glass and zoom into the atom, it is no longer thought of as a particle. It simultaneously lives as a particle and a wave, an electromagnetic wave. And it can have both interpretations. So he wrote this extremely famous, I think it's one of those where he had this leap of intuition, where he could write down the mathematics, because there was not enough scientific evidence at the time to justify it. It's one of those just a flash of insight kind of phenomenon. And just to, I know we all talk a lot in India about prizes. So each one of those I'm tracking were recipients of a Nobel Prize in Physics for that work. So now moving forward with this formalism of a wave equation, entanglement was postulated. And then, I'm sure you recognize the gentleman at the left. Everybody knows him. So he took objection to the fact that this phenomenon where mysteriously this equation says you flip something here and something else will flip far away, simply doesn't make physical sense. There's no intuition that justifies it. So he said there must be variables that are hidden that you don't know in the model that are coupling these two things. So he got together with two of his friends, Brodke and Rosen, and they wrote, in fact, a popular paper because of the first author, attacking this theory, saying that he called it, and at the time if he spoke loudly, people took serious notice, said this is spooky action at a distance. And this is called the hidden variable theory, which in the 60s got debunked actually. But the bottom line, this is not an easy thing to propose, nor is it an easy thing to verify. But lo and behold, many years later, work done from 64 to 1998 led these three people who did really brilliant experiments, because this sort of thing is very hard to verify, to receive the Nobel Prize in 2022, 3 years ago. So it's only 3 years ago that entanglement is accepted as a verifiable scientific fact. Through experiment, it was postulated, all sorts of indirect proof was there, but a direct proof is recent. So now, not to intimidate you, but quantum computers take all these things except for Einstein's objection and exploit it through a programming interface. So I can actually manipulate all these things through a quantum computer. And that's the brilliance of the engineering that happened in the last 20 years, which led to machines where you can actually set superpositions up through software, entangle things, and then if you are clever enough to write the right program, let the stack of entangled bits be processed, where when you touch the answer and read it out, you get what you want. So, and we'll see what happened there. So, an algorithm, a quantum algorithm exploits these features. Okay? And this is what everybody is after. Now, somebody in the opening of this session said that in 5 years we'll be looking at a quantum summit like this. It's happening now. There are summits around the world, the equivalent of this, maybe not 1,500 people, I don't know, but they are able to, and a year, our little startup could actually show how you have a problem that can be solved at scale. And therefore, sooner than you think, and that's the name of the company, Quant, we're accelerating the time to which these quantum technologies will use. And it's purely, we live in the software space, all the big giants, they build the hardware. And so, what is happening out there? The next two slides are largely due to McKinsey, the consulting company, and the Boston Consulting Group. They built these projections. So, you have, these are the areas where it's supposed to have impact. It's a long list. I'll get to that a little bit more towards the end of the talk in 10 minutes or so. But the opportunities are many. But how significant are they? So the scale on the y-axis is billions of dollars. So if you look at a modest projection, and this was done 2-3 years before generative AI, the AI piece of that was supposed to grow to $100 billion. And that's the quantum piece. Okay? And now there are all the other normal things like pharmaceutical drug discovery, pharmaceuticals, I'll talk about that, and other areas as well. So if you add it all up, that's close to a $250 billion at that time. But today, yesterday I heard, I haven't verified, that ChatGPT's market cap, people are talking about to be $1 trillion. Okay? I don't know if it's verified yet, but I heard. Now, that's $1 trillion, and this was when ChatGPT didn't exist. The quantum AI could be much bigger. So, these are areas that are just rising extremely quickly. So, is any of this real? Are people taking it seriously? That's a list of companies. Each column is a different type of hardware, technology, physics, who are investing in this area. So you can see, so the names you don't know are startups, but when I say startup, they're spent anywhere from $100 to $250 million building this hardware. And the big ones, of course, right? So we ourselves are partnering already commercially with IBM to validate what we do on their machines, and I'll mention that briefly in a minute. And also talking to other companies. IonQ is a very interesting startup out of Maryland in the US who are doing a different technology than IBM. And Google is invested in this. I didn't list it here, but Amazon also, but they're not as loud about it in the public domain. They're quite much more quiet. That amount of money, and this is old information from 2023, that has already been invested in startups in quantum. So there is over $100 billion invested worldwide in quantum computing startups. The number is a little big because the hardware companies soak up a lot of this. The hardware companies take up 600-700 million of this. And so the leftover for smaller companies like us is in the $10 to $50 million, but we don't need more than that at the moment, right? So, because it takes a lot of effort and people and cost to build these things, right? So, different companies have roadmaps on where this hardware is going. This is IBM's, one of the companies we use actively. So if you see from left to right, basically you just see those names, Falcon, Hummingbird, Eagle, Osprey, Condor, etc. Those are increasingly big quantum machines. And they're rolling them out every year, year and a half. And as they get bigger, you have more of these things, I said, called qubits. So you can use more of them, you can solve bigger problems. That's the whole idea. Okay? Okay. So everybody who's been building hardware, therefore, has a roadmap, and they're all projecting that by 2028, roughly, you'll have a machine big enough to really do whatever you want, in a sense, something at large scale. And so that's Google's roadmap. And so this sort of the march goes on. Everybody has a roadmap now. So it's a pretty predictable pattern. So just as this Mike did just now, qubits do the same thing. After a short while, in the middle of a computation, they kind of fade away and die. So what we just saw was a demonstration of a qubit in real time through the mic. So what happens with these qubits is because these electrons, let's say, are held so delicately in place, a change in an energy infusion to the electron causes it to go to a different state. But that can come from a tiny bump, the famous newspaper article that said a truck driving in New York 50 kilometers, miles away from IBM facility can send a vibration that can destabilize an electron. So these things are very, very delicate, is the short answer. And that creates a problem. So the fact that when they say I'll have 2,000 qubits in 2028 means that when I'll have 1,000 good qubits that will stay around with us for a while, and hopefully like this might last till the end of the computation, right? So that's the way a typical computation can be thought about. It's evolving in time. Those wire-like things are entanglements. The grayness means the qubit is fading away. And that's very common. So what we do in the company is instead of investing $200, $300, $800 million to make qubits better, we ask the following question. And that gives you an idea of how to approach this problem from different angles. We ask the question, how much does your algorithm really need to survive and compute? And so you look at the number of qubits it really needs through some mathematics, you understand the need, and what we show is you can typically live on a small fraction of the total qubits you think you need. So that's sort of like Archimedes' lever, where you use the leverage of the algorithm's need to live on a much smaller machine. So the name Axelacon comes from the fact that we can take a problem you thought you needed 1,000 qubits and show that you can live on, say, 200. This is a made-up number. And therefore, 200 you can get now. Therefore, you can deploy your commercial application 2 years before you thought you could. So you're accelerating time to deploy. And for a company, time to revenue. Now, I want to close in 5 minutes with the idea of machine learning and where the opportunities are. And broadly, I categorize this into 2 areas. Let's call it synthetic chemistry and generative AI. Okay? It's a very broad area. I'll allude to some in some detail, some of them, not all, because you get the idea. So these are topics within synthetic chemistry where the quantum computer is programmed to simulate a chemical reaction, for example, at scale. So you don't actually go to a lab with a person and mix things in a test tube and test, do extractions. You actually run a model of this in quantum software and conclude the cycle. So protein folding is very popular because none less than the Google arm that does AI in the UK released something which is called AlphaFold, a protein folding scheme. It's all machine learning. Now we're talking about classical, not quantum physics. Similarly, we have another aspect which manipulates genes, not proteins. And you also have molecular simulation, which is straight chemistry. And this has multiple applications. And then you have this big giant that has just emerged, generative AI. So in synthetic chemistry, I touch upon just one of them. And this is the AlphaFold success story. Over time, they could look at a staggering number and train them on 100,000 proteins, and they could find close to 3 billion folding patterns in these proteins that make sense. And this is classical AI. But then they hit a bottleneck. And then similar things are happening elsewhere in molecular simulation and battery design, where in the battery design area, in order to optimize, mostly motivated by EVs, electrical vehicles, the quality and the efficiency of the battery, you can do a lot of chemistry. But that can get very ugly in terms of environmental impact, all sorts of things. So what people do is they do AI-based modeling in order to understand these things. But all of them have a problem, and that problem, which is summarized here in the context of generative AI that all of you know well, or at least use it in some capacity, is there you have on the y-axis the amount of global CO2 that the electrical consumption of these giants consume, and those are the power numbers that these things use. And as you go, you're right now just talking about 170, less than 200 billion parameter models. Now we're talking about a trillion parameter models, and the growth is very non-linear, right? So, roughly speaking, numbers I've seen informally, they say that it takes about 2 months to train a model at that scale on a complete data center. You lock down the entire data center, train it for 2 months. And then you have a model which will play with for the next 2 months while you train the next model. Now you can't pipeline this on a daily basis because you don't have 60 data centers in a lockdown. And that's for one company. Now imagine the number of companies that are doing training on generative AI model, right? So the opportunity space that we see in a particular form of this generation, and that is synthetic image generation, creating images, which you have seen recently in some successful demos, I'm sure, where it's completely artificially generated with some seed image you get from somewhere. So this sort of synthetic generation is, you can see on the axis, basically a low FID score means that you're doing well. So as the y-axis became high, the hue dense, the red dotted thing, you can see it drops quite well. That's a quantum simulation of the image generator using generative AI. So there are data points like this that are coming about. And what we ourselves do, using our philosophy, is to be able to take a model like that, but show that you can deploy it using our techniques on a smaller quantum machine sooner. So we are not in the business of creating AI models, nor are we in the business of optimizing them in traditional AI. But we are in the business, at least as of a few months ago, in trying to get into taking a model which lives in the quantum world, or we can make it live in the quantum world, but by itself would have required a machine in 2028 or 2027. But you can live on it instead in 2025 or 2026. And you get the advantage that you don't have those very large power and resource requirements, and also eco-friendly situations, right? So that's the general philosophy of our company. And so can we make any of this really happen? So last year we did a study with an optimization problem. An optimization problem is trying to find a minimum or a maximum of something. And those are all names of different IBM machines. They name them after rivers and cities with varying number of qubits. And there is something in a quantum machine, because of the fluctuations of these qubits, which is called its fidelity, how accurate it is. Think about it as probability. So probability 1 means it's perfectly accurate, let's say, or 100% fidelity is probability 1. So the challenge said try to hit 99% on this machine. And using this method and making the qubit demands less and deploying sooner, we consistently hit 100%. And that's on real quantum hardware. So this is not a simulation. You actually can upload it in the cloud, invoke a machine wherever it is, and run it on IBM hardware. The other side of the story is what are we pushing to do? We're trying to take something that we say 1,000 qubits and say you can live on 200 qubits. 200 is now 1,026, 27, right? So so IBM has put out some benchmarks. The greenish blue curve at the bottom is when they will skip on the y-axis something called a certain quantum volume, the size of the problem. And it grows according to their projections along that line. Once you do our transformations to live on pure qubits, you get the purple line. That means you can move that point where you could get a certain volume from, I don't know, roughly 2025 to last year, which is when we did, right? So the entire philosophy of what we do is that living on other people's hardware, which is any of these, we're agnostic as to who makes the hardware. It's an abstraction that we work with. And last but not least, the domains of applicability that I mentioned to you are real, and we are concretely looking at aspects of machine learning. And that last application you saw, the image generation synthesis application, is at the front of all this. So this is happening now. The question says that can I translate the market size and technology opportunity into some sort of return on investment type estimate for a given enterprise. So first, a high level comment, everything we do is in the enterprise space. It's all what they call B2B. So we don't do B2C because it requires individual customers, right? Now, the numbers that start out in this, let us call it calculation, are speed up and let us say scale, the size of the problem. So I didn't say this here because it's all about AI, but there are non-AI domains which are where this is more obvious because the domains are mature and they already have revenue. So we are looking at a particular supply chain logistics domain which has a TAM, a total accessible market of about 12 billion. And we are now in the process of showing that a problem that they solve can be scaled in size by a factor of 100 and done 10 to 100 times over time faster. So that means they have actionable information which would normally take a few weeks to get to in a day on a much larger global problem. So you can imagine the domains, without going into all the details, airline industry, shipping, correct? All the heavy supply chain kind of industries. The same optimization problem also plays a role in the battery design. But I went into the more future forward-looking areas because the total TAMs in optimization are set. The accessible market is now well-defined. These are emerging TAMs. So for this forum alone, I picked areas, for example, drug discovery is a potential application, but the TAM on one of those tables was huge. Till, I would say, September, right, ChatGPT, before pre-ChatGPT, the TAM in that entire space was much smaller. Now, that company alone has a TAM that is huge, right? So, I picked areas where the markets are being defined for this talk. But there are mature markets where we are in-house working with companies like yours who have a customer base, but their problems are much less exotic and much more well-defined mathematically. So the markets for some of those areas are projections. Like drug discovery is a projection, correct? Protein folding, eventually personalized medicine is a projection. So I picked those because those are the more intellectually interesting future forward-looking areas for today's talk. And that's where AI and scale matter. But there we don't solve the problem at the base level. We try to take your AI solution and deploy it sooner at a larger scale, less cost. Now it's obvious to you that if something is 50 times faster, it's going to be cheaper. And if you solve something 1,000 times larger, also better. The exact dollar value, and that's a bit of a question mark, the more further out you are in the market.
Thank you, Dr. Krishna Palam. In the interest of time, may I request the audience to take any further questions offline? Thank you so much. In fact, I was thinking maybe 7 years. Within 2 years, we'll have to rename this to AI quantum based. We'll probably call it quantum machine learning.
We said in 2 years you might have to. We are a bit bullish in our company. We're accelerating. So I wouldn't be surprised if I was sitting with you this December to say let's do it next year. We're optimists. We're optimists.
Thank you so much. Thank you, sir. Thank you so much. We're now at the end of the conference, but before we end the conference, I would like to call on to the stage a very special person. I think this is already imprinted to all of our minds. May I invite Professor K.K. Babu from the National Institute of Fashion Technology, NIFT. If you're wondering what has NIFT to do with AI days and everything, everywhere you're seeing the logo over here, everywhere you're wearing the shirts, volunteers, everybody, everywhere the logo is there. It was designed by Dr. K.K. Babu. Sir, if you can just please come on to the dais once. Just one minute. Thank you so much, sir. This is a wonderful thing. In fact, we're thinking we'll use the same logo to the center, for the center we've just spoken about as the Center for Research and Development of People-Centric AI. And I think nothing encapsulates this better is what I thought. He said, no, Praveen, I have a better design. You have yet to look at it. Thank you so much, sir. Thank you for doing this. And I'll ask you to stay back. We are at the stage where we're doing vote of thanks. I'll first do the formal ones. First of all, thank you to the Department of CSC, University College of Engineering, JNTU, Supriti ma'am, if you're here, may I request you to come onto the stage. Rajni ma'am, Patnajarani ma'am, any of them, if you're here, please do come onto the dais. And JNTU, to the Vice Chancellor and to the University who have provided us with this thing, with this venue. It's wonderful. Thank you so much. To our supporters, Anurag University, Anurag, if you're here, please do come on to this. If you're here, Anurag University has been giving support to this thing. Anurag University, Meta is a supporter of this conference. We have Hitam, Sridevi College, and a lot of JPNC has also been a supporter of this conference. In addition to that, the supporters and everything, you've seen the partners, you see the AIML partners as TechVedica and DigiQuanta. Thank you, DigiQuanta and TechVedica. CX and AI partner being OzoneTel, or visual media partner, OneBlink media partner, Hans India, and lots of others I might be missing because they're playing with full screen. I typically like to copy some of these things, but that's okay. Using some of this stuff. What made all of this possible is not just the supporters, not just these organizations I said. Naveen, we will show you on the stage anyway. You can just please play other behind the scenes as well. I wanted him to play the behind the scenes because there's a lot of work that has gone into it. We had 2,000 people. It was not just because Naveen was eating. Good. He doesn't want to say anything else. So what I'll do is I'll call everybody on stage. I'll first start with the person behind all of this stuff. Kiran is the founder of Swecha. Please come on to the dais. We'll start with Kiran, but with the whole team effort, might I call all the preparatory committee onto the dais. All the preparatory committee, Pratap sir, Nag, Srinivas Garu, Vamsi, please come on to the dais. And all our speakers who have made this possible. Maybe Raju sir, come on, please come on to the dais. Suresh Garu, all the speakers, Anand, Sarajankar, please do come on to the dais. Krishna Palamur, might I request you to please join us on stage. Please here. Come. All the preparatory committee, the Swecha Executive Committee, which has worked hard, Dr. Pavani, Divya, Manjusha, Sahiti, Super Bloom Studios, if you're still here, I don't know if Super Bloom Studios, I can see, yes, please.
to join us on this. Divya ma'am is coming over here. Naveen, if you can stop eating and come join us over here, we'll provide dinner for you separately. Where is Rajshekhar? Rajshekhar. Chaitanya, hello. Hello, please. We also have the birthday boy over there. One, happy birthday to Ranjit. Happy birthday, Ranjit. Ranjit has turned 45 today. No, 50? 50, yeah? Divya ma'am is saying, why are you revealing the real age right now? Sorry, Ranjit, should I say what? I shouldn't say your real age. Okay, Ranjit is not 45. Hey, hello, Chaitanya. Hello, please, somebody please escort Chaitanya onto the... thank you. Ramesh, all, Shashikant. The question that I was asked, everybody was asking me, how is Shashi still alive? I don't think he has slept in the last 1 month. Where is Shashikant over there. Okay, Shashikant is over there. Sini, please do join us. Srinivasan Damani, yes. Dr. Srinivasan Damani. That's why he's not coming onto the dais. Scale only, 77 to 80, I don't know. Ready for it. We'll have the mic, I have the mic. If we hit 80, then we'll go to 90, then we'll see if we can actually hit 100. Doctors over here, Suresh got 100 decibels, is it safe for the ears for like 2 seconds? Even I thought okay, okay. Volunteers, also all the participants, may I request you all to come here closer. We'll see if we can hit 100 decibels over there. Shall we all come here? Shall we all come closer here? Come closer. Let's see if we can hit. In the morning we tried to hit 100 decibels. Naveen ensured that we could not hit it because he was hiding a laptop somewhere there. He was hiding the laptop there. Now also we have to shout that side. See if we can hit. This was morning session. Okay, 5 minutes. Everybody, let's come close. Let's see if we can hit 85 to begin with. Should I be ambitious or should I say 80 decibels to start and then? Okay, they'll first try without the mics. What should we say? We, us, AI first a sec. We'll try Swecha. Okay, we'll all try Swecha. We'll see if we can hit. Keep it, just start it, Mali stop the one Jekalam, 1000. Okay. Just keep it started. Okay, I'm at 70. Hello. I'm going to turn off the mic. Okay, we'll hit 90. Okay, 90 is our target, everybody. On count of 1, 2, 3, we will say Swecha. Count of 1, 2, 3, let's all say Swecha as loud as we can. Let's see if we can hit 90 to begin with. Alright. 1, 2, 3. We're at 78. Come on. Where is stop akkale? No, it's showing imagine. Where is the ekkadundi laptop? Koncham dekkar teesukandi. Alright, we'll try once again. We'll hit at least 80 here. We'll hit 80 and we'll go. Okay? You're going only after you hit 80. Volunteers, I need you on the stage. We need to hit 80 decibels. Okay? We're trying once again. 1, 2, 3. It has been try with the mics. We'll try with the mics once. Last attempt we'll try. Hello. దగ్గరికి వెళ్ళారు వాళ్ళు. మైక్ ఎక్కడికి వచ్చిన మైక్ అక్కడికే వెళ్ళండి. అట్లా స్పీకర్లు మారదు. Okay, all right. Once again. Have your mics on. One last attempt. We'll see if we can at least hit 78.5. Mic. Right, everybody, please come to the mic. Come closer. All right. Ready. Please turn your mics on.
అది పనిచేస్తుందా?
One, two, three, I'm sure Naveen has made this.
I am sure it is because Naveen didn't want us to. But good. Photos. Please stay back for photos. All of you onto the dash. Let's have some photos. And then we can. And then there's tea and samosas available. All right. Once again, let's give a big round of applause to everybody. Some photos, please. Yeah.
Come on, now. స్వేచ్ఛతో పయనం స్వేచ్ఛతో పయనం స్వేచ్ఛతో పయనం.
To stay informed about the startup ecosystem, subscribe to My Startup TV.
A person, who needs no introduction, but again, please allow me to introduce Dr. Jaydeep Ganguly, not a physician because we have a lot of other doctors as well today. We are going to cover 50 plus years of work in 20 minutes. So we'll be flying by decades and minutes actually. But I want to leave with you, there's so much of hype and talk about AI. Some of it is good, some of it is not so good. That I wanted to take the opportunity to walk you through from the very early days, how it all started, because I happened to be there at MIT with, when all of these things were happening with Macy and Tabert and everybody else. And since then, what we are doing today is very, very different. And my first observation would be that I would urge you to consider that we don't know what intelligence is. So before we say something is artificial, we need to know what is the real stuff. If you talk to neurologists, and I am not a physician, I have deep interest in these subjects, so I study the brain as time passes. My knowledge is still deep, but I'll talk to you about how the brain functions for you to understand how our neural nets do today, to let you decide for yourself how the brain works, how neural nets work, how LLMs work. There's a lot of excitement because it does some amazing stuff, and that should tell you the future years are definitely in this space. But we don't know exactly what that path is, that I want to caution you. But this is the most exciting area because the fields of neuroscience, quantum computing, machine learning are eventually going to converge, as you will see. So without more, so let me start with this, the first slide. Now where do I point? Yeah, if you can say the next slide. This doesn't seem to work. Okay. Yeah, it's working, sorry. Yeah. So, the mid-80s to almost the end of 2000, almost, was all the era of what I call knowledge-based systems, logic. Somebody would put in the rules by hand, craft it, and the machine will get smarter and smarter, and eventually it will behave like a doctor, it will behave like everything, like the humans would not be needed. There was the 5th generation project of Japan, many of you may know this. None of this really happened. So there were projects at almost any university, which everybody was working in this space. And they did produce some remarkable systems. For example, some of you would know the IBM's Watson. I personally was fascinated by Maxima. I don't know how many of you know, because whenever I struggled with math, I would go to Maxima and ask it to solve that problem for me. So whether it's Bessel functions or anything, it sort of did expanded and simplified solutions for partial differential equations. So it was a lazy man's way of solving math problem. And this technology, ability to deal with symbols, reason, primarily through two mechanisms: forward chaining and backward chaining. Forward chaining was very much prevalent in Carnegie Mellon. They came up with languages like Oxford. MIT came up with Lisp as language for symbol processing. We used to call it my friends used to call it lots of imitating single parentheses. Because Lisp was famous for its
first brackets. And then there were people in Europe mostly were into propositional logic like Kolmar and others who like to believe that logic first order predicate calculus will solve everything, and that gave rise to the languages like Prolog. And for almost 2 decades, people thought this was AI, and it is not today. So all of us who did our PhDs in this era, and there were so many of them, we are pretty much obsolete, because none of this really is out there. Now, around way back, 1959, Arthur Samuel was given, he was basically a mathematician at Bell Labs, who came up with this idea of machine learning. And his idea was very simple. You put some data, put some model, and it will sort of crunch it and produce some answer, and effectively the machine will learn. That's what machine learning is, and linear regression and other forms of algorithms like Vapnik support vector machines, a little bit more mathematical. They were all in this field, but they were basically, it was like a statistical approach, you would say. It's really not intelligence, if you ask me. It's some data you throw in, and you crunch some numbers, and eventually it comes up with the optimal model. So that was that era. And then the math behind, I want you to be patient and not sort of be irritated by these very simple equations. Machine learning is pretty much one equation. It is your some objective function, which is in this case is an error, some model. The equation one is a model, a very simple linear model. You run some positive, what we call convex function, because it will always converge, and you keep on crunching and minimize, and eventually you will get an answer. And this is how the gradient descent, that as you start up with unknowns, theta 0, theta 1, which you don't know what they are, x1, x2, you keep observing, y1 you observe, you keep doing it. You go back to your school days when you fitted a line with a bunch of points. You minimize the error. It's very simple elementary arithmetic, and that's all that's working in neural nets. You'll see that later. Now, interestingly, and I'll always go back to the brain actually functions like that. It does backward propagation. But let's wait for that slide to see why that is not that simple. But there is obviously a way when we make decisions. If you look at the brain, by the way, is a very complicated thing. There's a prefrontal cortex, there is amygdala, there is hippocampus, it's a zoo, 80 billion cells. So each part of them actually function differently. And here we have a very, very simplistic model which says we are going to regress through this and find a model. So that's the beginning of the machine learning. And not everything is a number. Sometimes it's binary, yes and no. So there we tweak this a little bit to this formula, and there for people like who are a little bit into mathematics, they'll immediately realize that we get to something called log likelihood to force the answer to between 0 and 1. So it's very elementary stuff really. That's all there is to it in the world of ML. Either of these two equations are working, whether it's neural networks, whether it is GPT, whether it is reinforcement learning, whatever you say, machine learning is only classification. Don't forget this one statement. ML is classification, classification, classification. When I say 10 words, what's the next word? It is one word out of the dictionary, which is typically 2000 words that we use. So it's a classification. 2000 classes, you pick one class. GPT, same story. Decision trees, same story. So ML is classification. ML is not intelligence. Okay. Now, let's proceed forward. This is the first part of our discussion. And we come into some very elementary concepts. Obviously, you have to do correct fitting. Some of the words are like overfitting, underfitting. Means that if the model is too simplistic, it will do an underfit. You're trying to fit a circle with maybe just a straight line. Obviously, it's an underfit. Overfit, you get it. You are trying to force a solution. Now, we don't know these parameters. We don't know how many features we need. So how do we know what to be fit? And that discussion will come back to this in the world of GPT and LLM and see how this has become such a huge problem. So the one thing that now at this point we know that an elementary linear model with some kind of objective function that you want to minimize, you will run into one of these issues. Either it's an overfit or it's an underfit. What's an overfit? Well, you have a cubic function and you are trying to fit something which is an 8th order or 10th order. And you can do that because you have so much data. And the reverse is what? You have actually a parabola and you want to fit a straight line. The problem is you don't know. The machine doesn't know what that curve is. So, and this will become, I'm spending a minute here because you'll understand how this shapes in GPT. How that becomes a formidable problem in generative AI. Most of people are overwhelmed with generative AI, but that will come back to haunt you in the world of generative AI, this particular slide. Now, next is the last slide, which is mathematical. I promise you there's only one. That machine learning, I said, is all about classification. So not everything is continuous. There are groups of things. So way back, Claude Shannon, everyone would know him. He came up with the concept of entropy. And what that really means is that if there is order in the system, entropy will be low. It's a thermodynamic concept actually. It's kind of common sense. There's a lot of, like for example, if you don't know anything what's going to happen tomorrow, that means there is no probability of, you really can't say anything with any probability. That means there's a lot of entropy. It may rain, it may not rain, it may flood, it may not flood. So nothing is known. So there's total chaos. That concept is Shannon's entropy. It's typically used in something called a Prelog Q format. What the name is after the gentleman. Very simple concept to Hilbert-Leibert divergence. That you pick a model and you see that formula that you last line and you see how it matches with your reality. See the divergence. If the divergence is 0, that means you got it right. If the divergence is huge, that means your model is not good enough and you keep iterating. So why do you need this? This you need in those classes of problems where it's classification. So we end the phase 1 of, I talked about the decision tree. We talked about regression. So you now need to come up with decision trees. Because that's another, we call decision trees also as artificial intelligence. At least we used to claim that once upon a time. Now, many of you would have played with XGBoost. It's a beautiful algorithm, very simple one, works great. If it is like 10 or 12 lines of parameters and very simple code, less than a page, works wonderfully. And all it does, it does something like this. That if I'm tracking soccer games and I want to make sure that how do I structure them, the tree, do I group them by the teams when they play in the morning, or do I group them they play in the morning in the local, in the what they call home and away? How do we group them so that the information comes out very, very lucidly? And that's where we apply this entropy concept. The formulas that you saw there, you would like to crunch through these very elementary numbers and come up with an information gain, what they call, and see the one that has the highest information gain, you would want to organize your tree, your so-called tree that you see in Excel or anything in this format. So classical AI stops here. It comes into using regression, some model, and classification. So that's the end of 20 years of work. And obviously there's a lot more, but I think you get the sense. Then we move on to the world of neural nets, which will lead you to LLM. The neural nets, around 2000, when Hinton showed in the ImageNet conference the beauty of the CNN algorithm, and Hinton is actually credited to this gradient descent algorithm and the variations of that, and showed that the enormous capability of machines to recognize images. And it did a pretty good job. I mean, it could tell varieties of cats, varieties of dogs. And you will see later that while this was very nifty, it took enormous computing power to recognize. The amount of training that had to be done is mind-boggling. Now, but then that spawned a great interest in machine learning through neural nets. And today, for example, when you use Alexa or when you use Netflix, you will see all these neural nets making recommendations for you. So all of that is powered by the so-called deep net. This is interesting because by the time in the late 70s, 80s, it was completely discredited initial and then kind of came back. And now, all of you know this neural net stuff. I captured it in one slide, very elementary stuff. What you see here on the sigma sign is that a bunch of inputs are coming in, and theta 0 to theta 1 are the weights. You multiply them and apply a function, and I'll come to why we have that function. That function is given below. It looks like a S-curve. There are 3 of them, sigmoid, hyperbolic, and rectified linear. So essentially it's a threshold. So when you multiply all those summations and you pass to that function, it crosses a threshold, then you get the next value. If it doesn't cross the threshold, it doesn't. And it propagates. So you have this incredibly complicated network. And again, you do the gradient descent that I talked about earlier. And all of you are probably familiar with it. You don't even really need to know. Most of the software will do it for you. And you crunch backward, the weights will get adjusted, and that's a neural net. Now, does it converge? Nobody knows. Actually, in many cases, it doesn't. And why doesn't it converge? Because most of the time, the optimization, for those of you who are mathematicians, will immediately recognize it's a local maxima or local minima. So it's like saying, I went to see the to the Mount Everest, but I landed up in Nainital and I didn't see any other peak higher than me, I can't say anything. So I concluded I'm at the highest peak, when you're not. So that's the problem of this approach. And people try to solve it, we'll talk about it a little. But I want to spend a few minutes to understand this slide and the next slide. So what you see here as the sigmoid function is the activation function in the brain that once the threshold crosses, is fed into that function. If it crosses, only will it go to the next neuron, otherwise it is zero. And so, how do you know what the thetas are? You don't, you just throw in some random numbers and then you run experiments to see what it produces. It's completely supervised. Does it give the answers that you see? And that's exactly how LLM works, by the way. If it doesn't, you start changing the weights again. How do you change the weights? Well, you change the weights by the good old chain rule of differentiation. Remember that anything that I've talked in math here, you probably have done in grade 11. Probably earlier, I don't know, these days probably they teach it in class 2, I don't know, but given our competition. But this is the beginning of the math and pretty much all that is used. But here lies the problem. This is what the brain is. Now I have a deep interest in the brain, so I am not a physician. I know very little, so with that caveat, I will tell you how the brain works. What you look at the nucleus, that's a neuron. And neurons are connected to the next neurons by axons. In the axon, you see there's a junction between the two neurons. What you see is the synapse, which is blown up there. The synapse is the Greek word which means a gap. It is not a continuous connection. So first thing you should understand in neural nets is, if a signal is 1, and if it crosses the threshold, the next neuron thinks it's 1, multiplied by the weight. The next one goes on, so the signal will travel entirely. The only way you can flip on and off is a sigmoid function which simply says, is it going through or not? It's almost like a gate. It's not almost, it is a gate. That's not how the brain functions. The brain, the axon is the brain, the first part, the axon is an electrical signal. The electrical signal that comes to the synapse stops at the electrical signal because there is no connection. It cannot go forward. Understand the neural net and why LLM. All of this is coming from this. And if anybody is a neurologist here will immediately jump and say, will be excited at this. What happens when the electrical signal comes at the synapse? The synaptic junction sends a chemical message. The chemical message is produced by the electrical signals by 1000 plus genes. There are 1000 plus genes right there in the signal. How do these electrical signals proceed? The electrical signals start by what is called an action potential because of the difference between sodium and potassium. Inside the neuron is potassium, outside it's sodium. These sodium-potassium potential differences start the electrical signal. So anything that you see, anything that you do, anything that you hear, anything does is a result of this action potential. The entire brain, this is the Zuban of the brain, it only says action potential. Now the problem is, when the action potential goes to the synapse, how that signal will go out is not a single signal, it's a signal there on the right bottom there, all those fields. The very interesting thing about the brain is that the code that goes out is a sequence of signals. All of the signals are of the same height, amplitude. But the packing of the signals are different. The amount of information that is flowing out is enormously complex. There are people doing research on that, and I'll tell you how these researches are done. So our model of neuron is an extraordinarily simplistic model where it simply says a signal comes in, it goes out, but that's not what it is. When you hear a piece of music, first of all, your brain, we are making a neural network assumption that the neurons are uniform everywhere. That's not the case. The brain consists of distinct segments as what we know. The hippocampus, the hypothalamus, the amygdala, the prefrontal cortex. There are different parts of the brain. The brainstem is where all the chemical serotonin, dopamines are all generated from that. All of these things are used in the synapse to decide what kind of chemical signals are going. So you will immediately realize that this is a digital plus analog, whereas your neural network is completely digital. So neurologists will tell you what we have produced is more of a caricature, more of a toy, thinking that, oh, this is the brain. And neurologists don't even understand it, by the way. There are 80 billion neurons in the brain. 90% of the brain is water. 10% is actually used. Different parts of the brain are collaborating with different parts. So there is an objective function going on. We don't know. It's not that there's only one part of the brain that's doing the objective function. It's all over the place. We don't know which classes of neurons work together. The neurons differ. And now I think you will understand that the complexity and how this is different. There's a guy called Medanta Sur at MIT who does this, he's an electrical engineer. He does a lot of, I've been following him for a long time. He does work on understanding this, and the way he does that, he has instruments on photoluminescence and high-speed, studies on mice cells. So different parts of the brain lights up. There are videos out there, you can see it. So that's how he's sort of back calculating and saying which portions are working where, what are they doing, and is there a mathematical representation of that, right? So obviously this is way too complicated. And by the way, even before you go to the next step, there are people like Roger Penrose who believe that it's not only these neurons and synapses, but actually consciousness and thinking is part of a lower level quantum processes in the brain's tubules, microtubules. So this is like quantum computing, and I don't even understand that. There's no way to tell it whether it's right or wrong. So obviously, one part is that the brain doesn't work the way, like neural nets. Even this description, according to Roger Penrose, he thinks that there is a at a quark level, something has happened, quantum entanglement. If you really have to read his book, I think the book came out in 1999, and it's a viewpoint where he draws concepts from Gödel's incompleteness theorem, quantum computing, quantum physics and brain, and there are people like Max Tegmark who don't believe in it. So I just don't know. I mean, I'm an engineer. This is way too far out. We are not even here. So now you are here. Okay. Now let's continue. So what did the computer scientists do? Well, they did some hacks. We're good at hacks. We said we'll have RNNs. We are going to take the state from one to the other. Basically, all the weights will carry on to the next state. And then they realized, so this will be like you deal with sequences. Because earlier neural nets, I showed all the input coming together. Now it will come as sequences. But then we soon realized it doesn't converge. Many of you know, RNNs don't converge. They have the problem of vanishing gradients or zero gradients. And so this was given up. Then we did more hacks. We said, okay, there's a smart guy in Germany. He said, you will know, this works actually pretty well. LSTM, long short-term memory, that will have some gates. We introduced self-state and said, we're going to tweak with the RNNs and force it to forget something and remember something and suit. And it worked for a limited, and for example, it's intuitive to you. If you say Ram met Sita, that makes sense. But Ram met Ram doesn't make sense, right? So I will force that through neural nets at a self state to force that whenever Ram meets Ram, no, that's not a valid sentence. So that kind of, basically common sense reasoning. But then also there's another branch of subject that popped up. We can't go into details. Reinforcement learning. A very, very important part of machine learning is reinforcement learning. RL is how I believe the brain works. Now there's different views of thought. Imagine a baby. A baby looks at 3 cats and recognizes the next one is a cat. A machine has to be trained with a billion images of cats, a million images of cats for it to recognize. So obviously something is very different happening. And the very different is happening is obvious also from the fact that the brain is very slow. A brain works at max 200 cycles per second. Mine probably works much less, but anyway. And a computer runs at gigahertz. Just imagine. But a baby is able to say, a cat is a cat, within, as soon as some neurons are developed in the head, very quickly. A computer, you keep feeding forever and it doesn't. Why is that? Because of the information content. The content that after the synapse what signal goes out is far more enriching information than what goes out of a neuron in a neural net. Remember, your brain is probably 1 kilo. 80 billion neurons in 1 kilo, which is less than 2% of your weight. Yet, it consumes 80% of what you eat, energy. Fascinating numbers. So, all the stuff that you eat, all the pizza, cokes that we eat is all going to fuel the brain, basically, right? And that's because the content of information that is created is of so high order. Whereas computers are basically doing very simplistic calculations again and again at a very high speed. That's the big difference. So now, we did some hacks and that worked, but then I'll move to the last part because we have time constraint, because this is the part where you probably are most interested in. All of that suddenly gave rise to the world of GPT. In 2017, this Google guy came up with a paper which caught my attention in 2017 itself because of its attention, with the title. I thought this is a really weird title for a paper. So it grabbed my attention. So I read it a couple of times. And then I found that actually in 2014, Benjo and one of his students, Benjo from, I think, NYU, and Badano had produced an earlier paper, very similar in the context of translating languages, I think German, where they introduced this concept of, I'll come to that, but what did they try to solve? All of us know that this is a problem of machine learning language. We went to the bank and learned of his bank empty account, after which we went to the river bank and cried. Now, a machine will be completely flummoxed, right? This is the problem of language. And that's why we talked about neural nets, that's why we talked about LSTMs. None of these really work. And people who worked on classical languages like Barbara Liskop and before that Chomsky, and both of them at MIT, they had a completely different approach to language. Suddenly the neural net guys came and said, LLM guys and came, we solved the problem. Did they? So let's look at that, because in these days, if you can't say GPT, you are not very smart, right? So we have to say GPT. So this is what GPT is. GPT introduced a few very interesting concepts. Simple concepts, elementary concepts. The concepts are, these are the last 3 or 4 slides. After that will be a master of GPT and LLM. And you will see that this is now democratized. Everybody in the world can build these things. It's not just big companies with, all you need is a lot of server machines. You have to also, earlier we talked about neural nets being fed data, then they said one after the other. Here they introduced the concept that I will provide positional embedding. That means where do these nodes out? Where do these words walk? So he went to the river bank. Every word he went to the river bank in a set of bits will also encode where that word exists in relation to the others. So it's actually a positional embedding. For the first time, they introduced that. They copied the concept from good old databases. Query times key must give value. For anybody who's coming from the database world and relational database will immediately recognize that query key value are nothing but database concepts. Query dot key must give me the value if I got them right. We'll see how that. Then they use the concept I'll talk about attention, information prevention and normalization and decoding. Very simple ideas. Let's see how this works or does not work. So first thing, the words that they come in now, they're coming serially. Words are not letters, words are embeddings. All of you know that. There's vector representations of some numbers. What we do, we create 3 arbitrary matrices, weights, neural nets, query, key, and value. What are the weightages of those? We don't know. Arbitrary. The idea is that if I do Q dot the input, whatever is coming in, it is a query representation of that same input. It's not the input, but the query representation. Bear with me for a second. I do that also for the key. Obviously, these are all wrong because your weights are wrong. You did the dot product, you got something, then you got Q and K. If you did a dot of those two matrix multiplications, you would get the value. Now, the value is also wrong, but hopefully they'll get trained. How will they get trained? So now, I have this embeddings coming in. I did the multiplication, and no, I don't do one representation Q, K, and V. I actually, V you don't create, V is generated. Q and K, I create 4, 8, multiple random matrices. Because we don't know what to start with, we create with multiple. So this is called multi-head attention. Why is it called attention? Query.key is the attention. How many of the K's and Q's do you do? 8 of them. Why did they do 8? Because that's what the Google guys started with. There's no reason. You did that, and then there's a technique for collapsing them to make them linear. Now you've got 8 results. Intuitively, it makes a lot of sense. if I tell a sentence, it's very hot today in Hyderabad, and if I ask the same question to 8 people or 10 people, their reactions will be different in their mind. There will be 10 interpretations, some of them similar, some of them not. So, the language assessment of this sentence cannot be led by just one query and key, and that's essentially the idea, that we'll have multiple of those. And there are some very elementary matrix multiplications and coalescing of these that will result in one final output multi-head attention. And what that attention is actually very simple. It is you can clearly see, it's almost like a masking, I'll give an example after this, but also they did another nifty thing. They said after this query.key, they would add back the original positional embeddings back to it again, because there's no mathematics behind it. Why? They just felt like. Because they would think they've lost the original positions of those words, what they meant. So while I have the intent captured, I'm again adding back the positional encodings, and then they do some normalizations, because this matrix has some are big numbers, some are small numbers. So you normalize by standard deviation and mean, and add a little bit below that 0.001, because sometimes if it goes to 0, it will blow up. So you will get a new matrix. So this is your multi-rate attention matrix, elementary math, right? You would get a matrix like this. And if you stare at this matrix, when you play the Game of Thrones, you will see the diagonal is very high. Why? Because it's most relevant to itself. After the crunching of this KQ, when you do all this matrix, this is like the Sobel matrix in image recognition, filter rather. Here, you have the words which are most relevant will pop up and higher numbers, and that's your attention. So, for example, the word is pretty much 1 to itself, because the word is most relevant to itself. So, when you say play the Game of Thrones, you will say the word the is not so important, so it's mostly 0. But when you say, some word like game, when you play the Game of Thrones, you will see correlation between game and thrones, if your query and key were trained properly. So that idea is out there. And then what you do, the rest is very simple. After you do this stuff, what you do is, you take the Q and K from the decoding part of the story. Remember, this was the decoding part. We started off by saying the left part is decoding. Left part, that is decoding. Position and embedding, multi-head attention, then again added a normalization. Now you got the Q's and K's, which is fantastic. And then you take it to the other side and you're all done. You take it to the other side. Now you have to produce the next word. How do you do that? You simply mask the attention matrix to zeros of the words that you haven't seen yet. Repeat the same process. So basically what you do after that, you will crunch to this number. Okay, I'll just stop here and take some questions, but essentially right at that step, after you got the K's and Q's and you did the dot product and produced a value and did the same old stuff again here, and eventually at the last layer, you are still doing a softmax, which is meaning picking a word. a statistical most relevant word. And so you now see that there goes your intelligence. It's at the end of it as a statistical machine. And it picks up a word. So you feed Wikipedia, it reads one after the other the words. After reading 10 words, it predicts the next 11th word. As long as it gets it right, it continues. If not, it goes back an iteration and keeps on changing. This, by the way, at this point is billions and billions of parameters with so many neural nets all over the place. And so eventually they'll get it right. But now, here's the thing, the last slide of my talk is, So GPT does not replicate human cognition. First thing we should understand. It differs from human cognitive process. It's just a statistical weight of one word with the other words. It's almost like saying, I am going to fit all the curves in the world with one parameterized equation. You know, and anything that you throw at me, any equation, parabola or whatever, circle, I'm going to take this one equation, which has all these weights, and it will give you the answer. So it is at best a weighted solution to that. Number two is that it will be prone to errors. What we love to say in the industry is hallucination. There is no hallucination, it's an error. It is statistical error coming out from picking a softmax. Remember, at this, then you will understand, GPT doesn't understand what an African elephant is. It knows Africa, it knows elephant. It doesn't understand African elephant because the elephant is the softmax of the previous state. It doesn't understand a Bengal tiger because it knows Bengal. It has seen many times Bengal and then tiger. So it will say Bengal tiger, but it has no notion what a Bengal tiger is. So, but it does jaw-dropping things. That you guys have seen it. And that's because, and nobody knows why. That's the beauty of it. Because statistical, basic statistics will tell you any overfitting will give you bad results. But what is very interesting in GPT is, as you fit more and more data, the results go up, then it goes down, then again goes up, and then again goes down. Why is this behavior happening? Nobody knows. So use GPT at your own peril, but I think you now know the opportunity is understanding the brain functions more, translating into neural networks which mimic the brain really, if you understand that, and add real computational processes, the convolutions that are happening inside the brain, the image processing that are happening, realistic modeling of those things are what will shape the future with the computing power that is arriving at our doorstep. So this journey will continue and it will be, we just don't know which way it will go. But hopefully, with this I'll stop, and I know I'm over time, but hopefully this was interesting for you. If there are any questions, I can try to squeeze in a few. It is not a language model. It is a statistical grouping of words. And if you have seen many of such examples before,